Yeah, so good afternoon. I have the honor to present you about the Threat Group. The Threat Group is an industry alliance standardizing wireless connectivity for buildings. We're a group of 150 members worldwide. We are end product manufacturers like an Osram. We have silicon vendors and RF module manufacturers. We have network stack suppliers, we have consulting companies, and we also have a strong certification program. So we welcome test houses and already have 6 different locations where threat products can be certified. So let's imagine the use case. Let's say you're a company making wirelessly connected devices, or in general connected devices for the building. You want to be part of the IoT. You want to have your devices connected via the internet protocol, for example, to a cloud server your company is running, or use the internet protocol to connect to building controls in the building. And let's say your devices are devices which have certain resource constraints. So in lighting, for example, we have the situation that standby power is limited by law to 0.5 watts. We have also switches, wall switches, which are sometimes battery driven or solar driven, energy harvesting devices. So we need low power. And of course, we also have certain constraints in terms of cost. Now, what network protocol should we use? And indeed, there's not a lot of selection. When you want to be really internet capable, meaning IP to the endpoint, then there's not a lot of different options. And that was basically the reason why Osram joined Threat Group and why many companies joined Threat Group. We wanted to create a low power network which is really IP and allows IP to the endpoint. Protocols like BACnet or KNX IoT really connecting down to the ground, and the devices being able to connect to their cloud services directly using IP protocol without any translation in the gateway. So how does a threat network look like? It's a lot of end nodes. A typical Wi-Fi end access point has something like 20 clients. In a threat network, you have hundreds of clients in one network. It's a mesh network, meaning that every device talks to every other device to form a mesh and allow border routers or internet connectivity through multiple routers, taking benefit of lower radio strengths because the devices are more in proximity. So a threat network can have, again, multiple or hundreds of end nodes. Some of those nodes will be elected to be routers. The network autonomously decides which devices are routers. That's typically the more capable devices, the ones which have net power, connection to the power grid. And the network also autonomously selects a leader device. But if any of these devices break down, then the device will automatically select new routers or new leader devices. So there's no single point of failure in such a network. The network heals itself, which is a real strength of a routed mesh network. Then you will find typically border routers in such a network. Those border routers connect the threat network to other IP networks. So this will typically in a building be Ethernet, but it could also be Wi-Fi, or it could be LTE into a mobile network, or it could be fiberglass. Anything which talks IP can be connected through a border router into a threat network. So those border routers will then connect your threat network into your clouds or into your mobile devices or whatever you want for your application. So benefits of this architecture, I already said it, battery-driven devices is possible. In a threat network, there can be sleepy end nodes. Sleepy means they're most of the time sleeping, not consuming battery power, not draining the battery. They just pull their messages from a parent router, and the parent router holds the messages for them to allow them to run on very low power. Threat is a routed mesh. That means it's not flooding the network with repeating messages over and over again. It finds the optimum route. So when one node needs to connect to any other node, it will find the optimum route through a minimal but necessary number of routers. which decreases latency and also decreases power consumption and makes routing very efficient and data throughput more efficient. And again, there is no single point of failure. If any of these devices fail, they will, from a network standpoint, be replaced by another device which takes over the role as a router or as a leader. Even for the border routers, there can be multiple border routers in such a network, and then one border router could take over for the other one if such a device is going off power or for some reason not operating anymore. Another important thing is security and commissioning. There's no way a threat network is not encrypted. It's always encrypted. You always have MAC layer security. There's also not any shared credentials which can leak. They are always created for every network. And on the MAC layer, there's always this encryption. On top of that, on the application layer, there may also be a second encryption layer, which is DTLS, which is the packet type of TLS. You may know TLS when you use your web browser and talk to your banking web page. It says HTTPS. That's basically this protocol. That's TLS. In threat, we use a packaged way of that, which is called DTLS. So basically banking grade security, which is another layer of encryption on top of the MAC layer. And that's used to secure the traffic from one node to any other node. When you don't want that other nodes in your network, even if they have the network key, they cannot listen to this point-to-point DTLS traffic. That DTLS is being used also for commissioning. So Threat has a commissioning app which you can download from the web page. And this app would transfer the security materials to a joining node through this one-to-one DTLS secured channel. So let's make a practical example. Let's say we have a building controller from a vendor A, and we have a lighting end node. I'm working for a lighting company, so let's make it a lighting end node using DALI protocol as an end node. How would you do this today? Today you would have your BACnet controller talking through the Ethernet, talking through some building network to a gateway. That gateway would then translate the information. Let's say translate BACnet commands into DALI commands and move the information on the DALI bus such the lighting application can understand it. That's today's situation. Works fine, but only works fine if the gateways understand all the latest innovations on the application and can translate the messages from BACnet into DALI. It only works if things are perfectly standardized. Once you add something which is proprietary, it would have its difficulties. Also, when you add another type of application, now let's add a wireless one with Zigbee, you would need more gateways. So let's say if you add a Zigbee device, you would add another gateway. The gateway would essentially do the same. It would translate BACnet messages into Zigbee messages and transfer it to the end node. Here it's a vendor C application. Could be any application, let's say a door lock. That could be also integrated into that network. The issue with that is obviously you need a lot of gateways and you have a lot of translation from one language to another language. And when your network grows, you will have to maintain all those gateways. When you add proprietary functions, you will also have to maintain your gateways to support these proprietary functions. If vendor X doesn't support a specific application, you need to add your proprietary gateway to make it happen. So this is all good reasons why you want to be IP in your network. IP works completely different. You don't have gateways, you only have routers. The difference between a gateway and a router is a router doesn't need to understand the application language. It doesn't need to understand the semantics. It only transmits data, and it does that with a highly standardized protocol with Internet Protocol. So it only understands the source address, the target address, and the routing protocols, and it will be able to connect everything with everything through every IP-capable physical layer. And the good thing is with Threat, now you have a low-power mesh network, which also lives on this IP and can be integrated in such an IP network. So that means you can also have a secure end-to-end communication. remember, in the gateway situation, the gateway translates the messages. In order to translate something, you need to understand it, so it cannot be encrypted. In an IP network, you can have end-to-end encryption because there's nothing in between which needs to translate something. It's just a series of bytes, and both ends talk the same application language. And in between, there can be a nicely encrypted message flow, which is very difficult to hack. So being IP, this also gives you the benefit that it can not only talk to your building infrastructure, it can also talk to your cloud. Imagine you have a thermostat or a door lock or a lamp, and you want to use direct connectivity to a cloud for software upgrades or for some additional service functions which are not supported directly by your building. You can add, as a manufacturer of your connected products, you can add a cloud service, and next to your highly standardized building application layer, you can have your own application layer talking to your cloud to add more services and to add more functionality to your device. That's, I think, something which makes the internet itself very successful. In internet, on a computer, you have multiple application layers. If you think about it, you have emails, you have your web browser, you have your SAP, whatever you have, it's all basically different applications utilizing the same network. And with Thread, you bring the same flexibility to the Internet of Things. Yeah, again, also to the cloud, you have your end-to-end security. So specifically in the internet, you want to be safe, you want all to have your data encrypted, so you want to have DTLS as an encryption layer to transmit your data through the internet. So Thread really started in the home environment initially, but now it's expanding a lot into commercial buildings. It adds new features in its commercial extension, making Thread also the protocol of choice for large buildings and large installations with very many nodes, bringing IPv6 to constrained devices in buildings. And I think we all know that wireless connectivity has already been or became the standard network for office and IT. I mean, every laptop talks nowadays Wi-Fi. You barely know if you plug in your Ethernet connector. It basically just works with IP and Wi-Fi, and the same will happen in buildings. More and more we will see wireless connectivity also in buildings. 80% of the buildings we equip with our stuff today are already built. They're just refurbished. Wireless makes a lot of sense because you don't want to add more cables. So very important that we get a wireless technology suitable for commercial buildings. But there is real problems to do that for a wireless protocol. There's many actors in a commercial building. When an installer installs the products into the new building, there may not be a Wi-Fi, or there may not be the expert at site from the IT helping the person to connect this to the IT networks. So the installer needs a tool to verify his work, to prove he has done his work without having done a full network commissioning by that time. We don't have hundreds of devices, may have thousands of devices. So your network must be very scalable. We need to respect the professional installation circles. So when the device is installed, you cannot assume that you have access to the device. You don't want to climb up the ladder another time and scan a barcode. So this needs to work in a different way, in a way which is suitable for commercial buildings and large installations. And you have the requirement that multiple roles are respected and can hand over their work in a clean way. And you need enterprise-level security to convince your IT department these devices are really allowed to talk through their IT networks into clouds and outside internet. Yeah, another thing important for commercial networks is if we really have a lot of products connected, you want to share your middleware. If every vendor brings his own middleware, then this will be a nightmare in terms of servicing and making security updates. So you want to share your middleware and have one IP-based middleware for everything. With Thread, you can have multiple application layers on the same network. So even a mix of KNX, BACnet, and whatever you like is possible on the same network. So a typical network installation on a commercial building could have multiple meshes Wi-Fi mesh, Wi-Fi plus thread mesh. It can be connected to the cloud. It can be connected to mobile devices, basically everything which has an IP address. So to summarize, Thread allows you to migrate your devices, and that's even low-power devices and constrained devices, into a true IP ecosystem. And your application doesn't even need to know if it talks through LTE, Wi-Fi, or Thread. It just talks IP with application language of your choice. Thread supports enterprise-level security. It supports standardized ways of commissioning known from the IT industry. It increases the capacity also and the bandwidth, allowing also things like over-the-air software upgrade. It does automatic roaming. It would shift your device from one network to another one to allow the network grow. For example, when you define subcells, when your network grows. It respects the IT requirements. It respects the security requirements from your IT department. It has specific user permissions for the different roles in your network, defined by your IT department. And finally, it allows also a clean handover, meaning that commissioning process is split in different roles, and your installer, your network commissioner, your application commissioner can just do what he is responsible for. That all allows advanced analytics through the cloud. Thank you. Any questions? We have a thread panel here. I will be here for another half hour. If you have questions, please let me know. Thank you.